want to look at enlargement, shear, stretch factors under geometrical constructions 10. Okay, so here I've got an enlargement factor that I want to look at. I've got this image here where I've got A, B, C, and it's going to the image of A dash B dash C dash there. Okay, so what happens here, we want to get the enlargement factor. We want to get the enlargement factor K. So we'll say our enlargement factor K, that's the one that we want to find. So for us to get it, we use a formula where I can say from this case, using this diagram, I'm going to say this is my origin O. Okay, so I'm going to take the distance from O to A image. Then I'm going to take the distance from O. I'm going to take it from O to image dash there, that distance. Then I'll divide it by the initial distance of our OA there. Okay, or else you can take the distance from OC dash to O over OC there. Okay, so let's do that. So my formula is equal to OA image over OA, or else we can say it's OB image over OB. Okay, that's what we are going to do. And if you can notice that from the small triangle, which is AB there, we are having the image is the same, the image has got the same geometrics as the initial shape that we had. So the angles also will be the same. Okay, so this was our A, our B, our C, and these are our images. Okay, so it's the same. Angle here is 90 degrees, angle there is 90 degrees, it's the same. So the geometry will be the same. Okay, so let's try to find the enlargement factor for this one. Okay, so if I said it's the distance OA dash there over OA. So if I count the distance from here going up there, I will have 4 units. So I'm just taking the diagonals then. So I will have 4 units there. So it's 4 over. Then I go for my initial. I've got 2 units there. I'm just taking them diagonally. So I've got 2 units there. So it's over 2 there. So it means the shear factor here becomes the enlargement factor there becomes 2. Okay, so this is the enlargement factor. Okay, and if we want to represent this information using a matrix, we will have our enlargement matrix as our enlargement matrix will be in the form of, remember we said when we talk of enlargement, H is equals to its factor by identity, in identity there. So at the end of the day, we can multiply and we get our matrix, enlargement matrix as 2, 0, 0, 2. Okay, so whenever you find a matrix that has got these same numbers here, it means it's an enlargement factor. Okay, and when we have it like positive like this and 2, it means it's going up and it's going to be bigger. Then we can even have smaller, where I can have, for example, an H being equal to say minus half, 0, 0, minus half. It means I'll have a smaller, it's going to be halved, the image can be halved. Let's have a look at this one. So for this one, I can have my image in this form. It can be formed here. sorry, it can be formed like this, where I can have my image like this. It will be formed something like that, and it's going to be vertically inverted like that. So that's what we do. Okay, let's look at shear. When we are looking at shear now, for us to get the shear factor, we say our shear factor is K. Shear factor is K. We can say this is the initial image. This one is the initial image. So we can say that initial image, the C, I'm going to take C points there. C, going to C image, this one, okay, over O, which is this one, the origin, by C. Okay, so it's like I'm looking at the perpendicular distance of O to C, this one. Okay, that distance. So for me to get the shear on that one, I'm going to look at the, so it's like my OA is my invariant line. Okay, because we are not changing the x-axis position, but we are shearing in parallel to our x-axis. So I can have it as for this one, the shear becomes C to C. I've got how many points? I've got from C here 1, 2. Okay, so I've got 2 units there. Over O to C, I've got O to C, I've got 1, 2, 3, 3. Okay, so it means my shear factor is 3 over 2 over 3 there. Okay, so that's my shear. Okay, and if I want to represent that in the form of a matrix, remember our matrix of shear is 1, 0, K, 1. When the x-axis is the invariant, and it's also 1, K, 0, 1 when the y-axis is invariant. Okay, so these are the invariant lines. This one is not changing, that's where we have our x-axis, and this one is not changing, that's where we have our y-axis as invariant, and these are the shear factor. So this one, we said our x-axis was the invariant, it was not changing. Our OA there is remaining the same here. So at the end of the day, we have our x-axis. We are going to use this matrix. Okay, so at the end of the day, our matrix of shear will become 1, 0, 2 over 3, 1. Okay, so this is our shear matrix, which is our S. Okay, let's go on and look at stretch. Okay, now let's look at stretch factor. So our stretch factor, we are going to use this image. So we can find our stretch factor as, using this image, I can have it as our K being equal to OB image over OB, or else as OA image over OA. Okay, so I'll check how we do that. Okay, so I can have OA or B there. So for B, it's up there, so I can consider the distance from this as the distance that it is the invariant line for the B. Okay, so I'll be checking the distance from this as my O there, like that. Okay, I can call it P. Let's call it P. Okay, so I'll take it as P there. Okay, so let me change this one here because it's not coming from O, so it's P there. Okay, now I can take the distance of now of OB from this point to this point. What is the distance? I've got 3 units over the distance of OPB there, this initial B. From this point, I've got 1. So I'll write for the first one, I've got 3 over 1. Let's look at the second one for OA. for the OA, I've got the initial OA, this one, I've got 3 units again, and I've got how many there? I've got for OA, I've got 1 unit, so it's the same. So I've got 3/1. So what it means at the end of the day is that our stretch factor is now equal to 3. Okay, that's what it means there. Our stretch factor is equal to 3. K is equals to 3. Okay, now we can even write this in the form of a matrix. If we want to write it in the form of a matrix, our stretch matrix S is equals to H O O K, whereby it means that we can stretch, this one where we have H and K, it means it will be a two-way stretch through x-axis and y-axis as invariant line respectively. That's how we have it like this. So when, like in my case where I had my x-axis as invariant line, I'll have my stretch matrix as 1, 0, 0, and 3. Okay, why? We are saying this one is the x values and these ones are the y values. So if the x values are not changing, so it means the x-axis is the invariant line. Okay, so this becomes our stretch factor. When we have our y-axis changing, s is equals to 3, 0, 0, 1. Okay, like this. We can have it like this. The y-axis will be not changing, so this becomes the invariant line, and this is our stretch factor. Okay, that's how you do. But when we have like this case where I said we have H and K, we can have an example of 2, 3, 0, 0. We have got stretch factor 2 with our y, stretch factor 2 with our y as invariant line. Then we have our stretch factor minus 3 with our x-axis as invariant line. So that's how you'll be ending up stretching your image. Otherwise, bye bye guys, let's meet next time in geometrical transformations.